Hi everyone! Today we're going to continue chapter 7, which is all about solutions. Last time we talked about how solutions are made up of a solute and a solvent. We also reviewed some solubility rules, and then we also discussed how solutes can become more soluble at higher temperatures, except for gases. And we also talked about unsaturated versus saturated versus supersaturated solutions. So today, let's start by discussing how to increase the rate of dissolving for a solute. So we have a few options here. The first one is to crush or grind the solute. So for instance, some compounds can be quite clumpy, for lack of a better word. So for instance, let's say we have this huge clump of solute. It's going to be really difficult for water to attack that and break it down. So what we can do is start by grinding this up into smaller particles. This is going to increase the surface area, and that will allow the solvent to better dissolve the solute. Another option is to heat the solvent. So for instance, last time we talked about adding sugar to iced tea versus hot tea. And adding sugar to iced tea, it doesn't dissolve very well or very quickly, but if you add sugar to hot tea, it dissolves really well. So the reason for that is if a solvent molecules are at a higher temperature, they have more energy. So they're going to move faster and then have more frequent collisions with the solute, which will help it dissolve. And then the last option is to stir or agitate the solution. So let's say we have a beaker with water and we add our solute, and let's say it all kind of bunches up on the side over here. So water will be able to dissolve some of the surface particles, but then it becomes saturated, so it can no longer dissolve the solute. So we need some of the unsaturated water on the other side of the beaker to move closer to the solute. So we can stir the solution or agitate it in order for that to occur. Now there's a couple of ways we can do that. We could stir manually with a glass stir rod. So that's just literally like a stick that's made of glass. Or we can use a magnetic stir bar. So what we would do in that instance is put our beaker onto a hot plate. And we would want a hot plate that has a stir function. And then we would drop a magnetic stir bar into the solution. It almost looks like a little pill or capsule. And the hot plate has a magnet in it. So when we turn up the stir function, that magnet rotates, which then rotates the stir bar. So as the stir bar is turning, that agitates the solution and mixes everything together. Okay. So a while ago we talked about endothermic versus exothermic solutions. And remember that in an endothermic process, heat is absorbed. So we could even write heat as a reactant. So you can see the equation here. We have solute plus solvent plus heat. And heat is one of the reactants because it's being absorbed. And then that will create our solution. So as an example, down below endothermic, we have a couple of figures. So we're adding something called ammonium nitrate to a beaker of water. And what's interesting about this solution is once we add the ammonium nitrate and we mix it with the water, it actually absorbs heat from the surroundings. So what ends up happening is we are going to feel a cool solution. So this is what's in ice packs. So ammonium nitrate reacts with water and then it absorbs heat from its surroundings. And what we feel is coldness. So heat is being drawn away from our hands and it feels cold to our touch. But then in an exothermic solution, heat is released. So we can write that as a product. So you'll notice in this reaction we've written solute plus solvent forms solution plus heat. So one reaction that is exothermic is the reaction between sodium hydroxide and water. So if we add solid sodium hydroxide to water, we're actually going to feel heat coming off of that solution. So it's going to feel hot to the touch. So when we make different solutions, just remember that there is energy involved in the form of heat. All right, so we do need a way in order to quantify how much solute we have in a solution. Because for instance, maybe we want to use that solution to make other solutions. So maybe we want to have a really concentrated solution and then dilute it to something else. So solution concentrations will express a quantitative relationship about the amount of solute contained in a specific amount of solution. So there are a couple of different ways to express concentration. We could either use something called molarity or percentage. Now, most often in chemistry, we use molarity, so we'll talk about that first. And then I think in a separate lecture, we're going to talk about percentage. Now, down below, we have a figure of a solution here that's kind of orange or yellow. And that could be our stock solution. So it's highly concentrated. So what that means is there's a lot of solute in that flask. But then what we could do is take a small amount of that and add it to a larger flask and then fill that flask up with water. And that's going to create a more dilute solution. So that means we have a small amount of solute in a large amount of solution. Okay, so it is important to know how much solute you have in your flask because, for instance, reactions do depend on how much reactant you have. So it's important to know how much you're starting with. But then additionally, you don't want to use a highly concentrated solution in certain situations, or maybe you don't want to use a solution that's too dilute. So there's different scenarios where you should know how much solute is in your solution. All right, so how do we calculate molarity? So the molarity of a solution expresses the number of moles of solute contained in 1 liter of solution. And down below we can see how we would express this mathematically. For molarity, the unit is just a capital M. So I'll write that down below. Oh, misspelled molarity. Let's see. There we go. So this is a lot easier to write than the units that are shown for molarity. So molarity is equal to moles of solute over liters of solution. So instead of writing moles per liter, we can just write a capital M, which is a lot easier. All right, so in this equation, the number of moles of solute in a sample of solution is divided by the volume in liters of the same sample of solution. Okay, so let's do a practice problem where we try to determine the molarity or concentration of a solution. So in this first example, a 250 milliliter sample of solution contains 0.134 moles of solute. Calculate the molarity of the solution. Okay, so let's start by writing out what we're given. So we'll kind of organize the data here. So we're told that we have a 250 milliliter sample of solution, and that solution contains 0.134 moles of solute. All right, and then we're told that we need the molarity. So I'm just going to write capital M there for molarity. But we know now that that is equal to moles of solute over liters of solution. Okay, now looking at what we were given, we do have moles of solute, but instead of liters of solution, we have milliliters. So our plan, we do probably need to do a conversion here. So we'll convert milliliters to liters. And then we already have moles, so we can just plug that in. Okay, so let's do our quick conversion here from milliliters to liters. All right, so we're trying to get 2 liters. So we're going to put liters in the numerator, and then we're trying to cancel milliliters. So we'll put that in the denominator. All right, now how many milliliters are in 1 liter? And remember, milliliters are smaller. Okay, so hopefully you remembered that there are 1,000 milliliters for every 1 liter. Okay, so we're going to cancel the unit of milliliters, and we're going to divide 250 by 1,000. So that will give us 0.250 liters. Okay, so now we have all of the appropriate units to calculate molarity. All right, so molarity is equal to 0.134 moles of solute over 0.250 liters of solution. Okay, so if we plug that into our calculator, that gives us 0.536, and you can write moles per liter as the unit. That's totally fine. But again, it's sometimes easier just to write a big capital M for molarity. Okay, so not too bad, right? You just have to make sure all of your units are the right units there. Now let's do one more example problem. And this one might be a little bit trickier. So in this example, 9.45 grams of methyl alcohol, which has a formula CH3OH, was dissolved in enough pure water to give 500 milliliters of solution. what was the molarity of the solution. All right, so let's start out by writing what we're given again. So we're given 9.45 grams of methyl alcohol, so CH3OH. So sometimes this is written as CH4O, but alcohols have an OH group on them, so typically you'll see an OH on the end, and that's just again to indicate that it's an alcohol. All right, so now we were also told we have 500 milliliters of solution. Okay, and then we need to determine the molarity, which again is moles of solute over liters of solution. Okay, so looking at what we were given grams, not moles, but how do we go from grams to moles? Is that possible? Yes. So remember from a long time ago when we were discussing our flow chart for how to get from grams or moles of reactant to grams or moles of product, we just used molar mass to go from grams to moles. All right, so we'll convert grams to moles, but we need molar mass. So we'll have to do a quick calculation there. And then we also need liters of solution, but we were given milliliters. So similar to the last problem, we're going to convert milliliters to liters. Okay, so let's calculate the molar mass of methyl alcohol. All right, so we have a carbon atom, so that has a mass of 12.01 grams per mole. And then we have 4 total hydrogens, so we'll multiply the mass of hydrogen by 4. And then we have an oxygen, which has a mass of 16 grams per mole. Okay. And if you want to pause the video at any point to try this on your own, you can. All right, so if we add all of those together, we should get a molar mass of 32.04 grams per mole. So now we can use that to convert grams of methyl alcohol to moles of methyl alcohol. All right. So let's do that really quickly. So we've got 9.45 grams of methyl alcohol. And we're going to use the molar mass to convert from grams to moles. So since we do want to end up with moles, we'll put 1 mole in the numerator. And then we'll put the mass in the denominator. All right, so grams will cancel. So we're dividing 9.45 by 32.04. And that should give us how many moles? So I got 0.295 moles of CH3OH. Okay, so now the next step is to convert 500 milliliters of solution to liters. So last time we saw that there were 1,000 milliliters for every liter. So if we divide 500 by 1,000, we'll end up with 0.5 liters. Okay, so now let's do our final calculation, molarity. So we're going to plug in moles and On the denominator, we'll plug in our liters. So we have 0.295 divided by 0.5. So that should give us a concentration or molarity of 0.590 capital M for moles per liter. Okay. So this problem involved an extra step. We had to convert grams to moles, but we've done that a lot in the past. So hopefully at this point that's not, too difficult. But if you do want to review how to do those conversions, definitely make sure to go back and go over those lecture notes or lecture slides. Okay, so here's a solution slide there. So if you need to go over that later. So next time, what we'll do is step through how to calculate concentrations in terms of percent. And there's a few different ways to do that. So that's going to be another separate discussion. So I will see you in the next video.